Alright, we're Team 5 and we're proposing an internal fixation device. Internal fixation systems are used to provide mechanical support during the bone healing process. Currently, most of these implants are made out of non-biodegradable metals and they're designed to remain in the patient for life. This can lead to a variety of adverse effects such as patient pain and bone loss due to stress shielding, of which you can see an example on the right. Notice that the areas of bone around the screw insertion sites are less dense. So because of these issues, a lot of these implants require secondary removal surgeries, which is one of the most commonly performed orthopedic surgeries today. 42% of orthopedic surgeons recommend the standard removal of internal fixation systems, despite the risk and the cost associated with these procedures. And so this really highlights a need for a biodegradable internal fixation system that can avoid the adverse effects of permanent metallic implants while preventing the need for any sort of secondary surgeries.
As been stated, our approach is to design an internal fixation plate that will degrade at a rate that allows for proper bone remodeling. We'll achieve this through the use of a biodegradable magnesium 6 zinc alloy, and our choice for this metal is due to its preferable mechanical properties, being similar to that of human bone. The Young's modulus of human bone is 20 gigapascals, and our metal is close to 40 gigapascals. We'll be able to achieve a patient-specific tunable degradation rate to match the patient's healing rate through the use of a 2% PLGA coating. And this will prevent any degradation for the first 6 months while allowing for a 2.5 millimeters per year degradation rate after. The bone contacting surface site will have a high surface area which will allow for osteoconduction. This prevents micromotion for the first 6 months, which is crucial for proper remodeling. The plate will be held in place through the use of a multi-porous hydroxyapatite magnesium-coated screws that have larger pores for osteocyte infiltration as well as smaller pores for protein absorption.
When looking at the benefits and costs of a biodegradable system, we first look at no retrieval surgery. And so the benefits from this is financial benefits as well as safety. And so from the financial benefits side, patients can save upwards of $30,000 as well as a reduced burden on hospital resources. And on the safety side, 20% of retrieval surgeries normally lead to complications. And so by having a biodegradable system, we mitigate the need for retrieval surgery. And because our device is biodegradable due to the common metabolites, since both magnesium and zinc are both found in the body. And lastly, there's no longer a permanent implant, and this will eliminate long-term patient pain as well as eliminate bone loss due to long-term stress shielding effects. And when looking at the cost side, the degradation rate is of great importance as it could be a potential cause of cytotoxicity as well as systemic toxicity. And so by having a low degradation rate, you can have a low concentration of the magnesium and zinc ions in the body. And lastly, the last cost is getting FDA approved.
Current standard for bone fixation plates are devices made of high-strength metallic alloys. Those devices have the same problems we talked about with stress shielding and retrieval surgeries. The current biodegradable-based devices are PLGA-based devices. They avoid problems with retrieval surgeries, but they're very weak. They're weaker than particle bone and the magnesium alloys that we're proposing, and they aren't suitable for load-bearing applications. Currently being researched are silk-based devices. These have good mechanical properties in many aspects, but they're very weak in shear that makes them unsuitable for shear dependent applications such as screws.